This is Math 154, and we are beginning Unit 2. Unit 2 is the other half of Section 6. That's actually Section 6.1, and then the end, 6.7 through 6.10. And we'll be looking at the physical applications of the integral in this section. And we start here in 6.1, talking about linear motion. Okay. I want to start with just a simple, old-fashioned arithmetic or algebra problem. If a student leaves home and drives due north for 2 hours at 40 miles an hour, later drives back toward home due south for 1 hour at 50 miles an hour, find the distance traveled and the displacement. So just to draw ourselves a little diagram here, if we assume that this is the student's home, and they go due north for 2 hours at 40 miles per hour, then they would be traveling 2 hours times 40 miles per hour, right? The distance would be rate times time, 40 times 2, or a distance of 80 miles. Later drives back toward home due south for 1 hour at 50 miles an hour. So starting up here now, driving due south, again, distance equals rate times time. And in this particular case, we'd have 50 miles an hour times 1 hour, or 50 miles. This is miles as well. Okay. The two questions that are being asked are actually the distinction that I really want us to make here. The distinction between the distance traveled and the displacement. As far as the displacement, which I'd like to do first, what's going to happen here, and I'm assuming the student is traveling really along the same road. I drew them separately so we could see them, but really this is all one road, right? So they've gone 80 miles north, 50 back south, meaning that they end up 30 miles from where they started. When we do this, we think of our distance as what we might call a directed distance. If we consider our northward direction to be positive, we'd consider a displacement of 80 in the positive direction. And if we consider the southward direction to be negative, we would think of that as a 50 miles in the negative direction, showing us that we end up 30 miles from home, or 30 miles from where we started. That would be the displacement. The distance is how many actual miles were driven. And so in that case, of course, we've driven the 80 miles here, plus an additional 50 miles here. And mathematically, it's going to be to our advantage to think of this as not just 50, but more like the absolute value of the directed distance. So I'm thinking of this as the absolute value of a positive 80 and the absolute value of a negative 50, giving us a total of 130 miles of actual distance driven. Okay? That way we can consistently think of our distances as directed, rather than thinking, hey, sometimes we have the negative and sometimes we don't. The absolute values just take care of that for us. All right, we're going to work at this now until we get this into a calculus application. But we'll use these same concepts of distance as rate times time, displacement as the sum of directed distances, and the distance itself, the sum of the absolute values. So, just quickly in words, what is the difference between distance and displacement? Let's actually create ourselves a couple of little columns here. Displacement and distance. Okay. Just in words, as we said, displacement is essentially how far away from the starting point that you end up. So I'm just going to abbreviate that as how far from the starting point. Distance, on the other hand, is the actual number of distance units traveled, or how far we actually travel. For the displacement, we said we add the directed distances, so that it would include the negatives. And mathematically, if we pull out a little notation here, adding is summing. So let me use that sum notation that you saw back in Calc 1 somewhat briefly, but we'll be using it again. And we're going to add up what I'm going to call the d sub i's, where the d sub i's are the directed distances. And it's however many we have, right? If we have 2, then we'd be summing from 1 to 2. If we had 50 little pieces of distance, we would sum from 1 to 50. So in general, I'm just going to say we sum from 1 to n. All right, distance. For distance, we want to count everything as positive. So here we're going to actually have to add the absolute values of the directed distances. And so again, I can say this is the sum, and we'll again just say I is 1 to n, however many pieces we have. And this time we want the absolute value of the d sub i's. So just a little bit of mathematical notation there. All right. If our motion is all in one direction, how do we find distance? Well, in fact, what we're going to end up doing here, of course, is saying that, and let's do both distance and displacement. And I might as well just continue my columns here. As we set up here, distance and displacement are really just rate times time, or velocity times time. In actual fact, if I wanted to go back up here and kind of fix this a little bit to account for the directed distances, the time values themselves are always positive. Time only moves in one direction, forward, right? However, the rates or velocities could be considered to have direction. So I could consider, if north is the positive direction here, I could consider that a positive 40 miles per hour since it's in the north direction, and therefore a positive 80 miles. Whereas here, since we're traveling south, I could consider this rate a negative 50 miles an hour, and therefore the distance a negative 50 miles. Again, thinking directed distances. So let's go back here now and say, all right, if we go back to the idea of distance being rate times time, I could actually kind of fix this up a little bit, right? I could say this would now be the sum of those directed distances, which would be the rates times the times. And I'm just going to call that r sub I times t sub I. So distance equals rate times time. And for the distance where I want the absolute values, again, I can just change my sum, and I could say that's the absolute value. Oops, I'm sorry, of r sub I. I've been teaching too much Calc 3 lately, lots of vectors in Calc 3. There we go. The sum of r sub I, t sub I. With, notice the absolute values. I could have put it around both the r sub I and the t sub I, but t is always positive. Time's always positive. So our r sub I is actually what we're going to do the absolute value of. All right, in writing these, what assumptions were made, and could we get rid of any of those restrictions? Well, the first assumption that was made, and by the way, this is one we're not going to be able to get rid of, is that all of our motion is along one straight line, right? Everything was here either up or down. I didn't go in different directions, right? I didn't go left or right or on an angle or anything like that. So all motion is along a line. So we have two directions we can go, up or down if we're using a vertical line, left or right if we're using a horizontal. The second assumption that we made is that within each time interval, our velocity or rate of change was constant. right? So whatever time interval this was going to be for these 3 seconds or whatever, that velocity had to stay the same for that time interval. So the velocities, the r sub i's, are constant within each time interval. If you go back up to our picture again, just a reminder of what we mean here, for that 2 second, or hours I guess it was here, for that 2-hour period, the 40 miles an hour was constant. It didn't change velocities over that time period. Same over here for this 1 hour, that 50 miles per hour was constant. This one is a restriction we actually can look at easing up. Again, we have to stick with the straight line motion for now. We'll be able to get rid of that till Calc 3. But we can ease up on the velocity. Velocity. Sorry. If we allow our velocities to vary, then we actually know from Calc 1 how to handle that, right? To get distance, we know that we can actually, instead of adding up, we could integrate the velocity times the time. So if we allow variable velocities, what we can do then is say that if our position function is s of t, that's what we usually used, our velocity function, I'm going to call it v of t, is just the derivative of the position function, right? We learned that back in Calc 1. Now, as soon as we start allowing things to vary, we're into the calculus mode. And so we're going to say, instead of adding up individual intervals, instead we're going to integrate over this continually changing velocity. So I'm now going to say, once again, let's do a displacement and a distance. For our displacement, which was rate times time, we're now going to say, okay, that's the velocity, or s prime, times the time. And since we're going to end up integrating, our time interval is going to have to be shrunk infinitesimally small. So instead of a t sub I, I'm now going to call it a dt, just a tiny little time interval on which our velocity function can be considered to be constant. And we're now going to, instead of adding, we're going to integrate. Right? And we'll integrate from some starting time to some ending time. Same idea with the distance. Again, the rate, or velocity, is s prime of t, but for distance we'll have to take the absolute value. Okay. So those kind of fancy looking formulas are really nothing more than the old algebra formulas. Rate times time is distance. They're just now written in a situation where we can have a continuously changing time period, or changing velocity, over time. All right, with those two formulas in hand, let's look at a couple of examples. All right, so in this example 1, we have a jogger running on a straight road. So I get that a little bit clearer. A jogger runs on a straight road. Her velocity in miles per hour at time t hours is given by v of t equals negative t squared plus 5t minus 4. And in this case, notice that's already v, so this is already s prime. We don't have to figure out the derivative for ourselves. We were basically given it. All right, I'd like to graph the velocity function on the interval from 0 to 3. So just a regular old graph of this velocity function. And you can use Desmos or a graphing calculator to do that. So there's my function. And I'm only interested in the time interval from 0 to 3. And I'm going to leave negative 10 to 10 for right now. So it kind of looks like that. My goal right now is to determine when the jogger moves in the positive direction and when she moves in the negative direction. And by looking at the graph, that's fairly easy to figure out, right? Clearly, when we are below the axis, these are negative velocities. So, on this little window of time, the jogger is moving in the negative direction with a negative velocity. So v is less than 0, or in other words, we're moving in the negative direction. For t from 0 to whatever that point is, looks like 1 on here, I can double check that. And yes, the 0 is at 1. So from time 0 to time 1, we're moving in the negative direction. And then, of course, over here, all of these would be positive values of v. So our velocity is positive. And that would be from times 1 to 3. All right, so my goal next is to find the displacement of the jogger in miles on the time interval, and that's a typo, that should be from 0 to 3, and then interpret the results. So just a reminder, our displacement was simply the integral of the directed distances. I don't have to have absolute values or anything. So my displacement, just going to write my formula, integral from a to b of the velocity v of t, or s prime, whichever you want to think of it as, dt, which in this case would be the integral from 0 to 3 of that velocity function, negative t squared plus 5t minus 4 dt. All right, let's go ahead and do that integral. We would have negative 1/3 t cubed plus 5/2 t squared minus 4t, evaluated from 0 to 3, which is negative 1/3 times 3 cubed, 27, plus 5/2 times 3 squared would be 9, minus 12, and I'm getting 1.5 for that. So as far as interpretation, that means that over the first 3, did we give? I guess miles per hour, so this, over the first 3 hours, the jogger is going to end up 1.5 miles from where she started. So after 3 hours, the jogger ends 1.5 miles from the starting point. All right, let's compare that to the distance traveled, which is the next question. Again, I typo here, let's make that 0 to 3. In this case, my distance would be the integral from 0 to 3 of the absolute value of my velocity function. Okay. This is where I'm going to use the results from part A. I will note that if you're allowed to use a calculator, then you can certainly just type that in, and I might do that to check my answer anyway. But if you have to do the integrals by hand, and this whole chapter really is on applications of the integral, so we'll typically integrate by hand at this stage. In that case, we're going to actually need to know the information that we figured out in part A. We know that our velocity function is actually negative from 0 to 1. So when I write my integral from 0 to 1, if I were to integrate the actual velocity function, that would give me a negative result. For distances, I want everything to turn out positive. So I actually want the opposite of that, or if I want to, I could just say absolute value, but I'm going to throw the minus in there. That's minus a negative, giving me a positive contribution to my distance. Then from 1 to 3, we know that the velocity function was already positive, so I don't have to change it. So if I were to distribute through here, minus this negative, I could make that a positive, make this plus, minus, and plus. And I end up getting 1/3 t cubed minus 5/2 t squared plus 4t from 0 to 1 plus a negative 1/3 t cubed positive 5/2 t squared minus 4t, and that goes from 1 to 3. I suspect at this point you're all perfectly comfortable plugging in the numbers, so I'm going to let you work that arithmetic if you'd like. But when I did that, I got 11/6 out of this one. And then I got 10/3 out of this one, for a final answer of 31/6. And that would be in miles. Now, I want to label these a little bit because as we go to draw our picture, it says label, draw and label a sketch. These values, these individual values are going to be important, right? Originally, this came from where our jogger was going to the left, right? We made it the opposite of a negative number to contribute to distance. But this distance originally was really going to the left, if you consider the left the negative direction. Whereas this one was going to the right. So if I want to draw a sketch of my jogger's path, it would look like this. I'm going to consider the starting point to be 0. It's arbitrary, right? Wherever we start, we're calling that x equals 0. And I'm going to begin by showing that this person's going to go left 11/6, or minus almost 2, right? So on my number line, I might label that negative 11/6. Then they're going to go back to the right 10/3. And keep in mind, because the final displacement is 1.5 or 3/2, we know that when we end, we're going to end up at 1.5. That was my displacement. So 1.5 about here. And that's 1/2 or excuse me, 1.5 or 3/2, where we end. The length of that part to the right is 10/3, and the length of this part to the left was 11/6. And that shows the specific path that this jogger ran. Now I chose to show my negative as to the left and my positive to the right. You maybe remember on the previous page we used negative as down and positive as up. It doesn't really matter how you define positive and negative, but those are the most common choices, either up and down or left and right.